Hi guys, good morning. So as you can see, today I'm speaking in English, and the reason for that is because, for a change, we can, sometimes swap languages, and we are in a physics department producing international grade research. So I thought, okay, you guys are all graduate students, most of you at least. So why not, sometimes to train, break the routine of speaking Portuguese. We can speak in English, that's one thing. And the other thing is that I can use this for other presentations, for people outside Brazil, which is also good. It's a good advertisement. It's a good way of showing that we're thinking about stuff, interesting things and stuff like that. So anyway, today I'm going to shift a little bit in interest. It's going to be maybe a little bit bigger lecture. Okay, I got enthusiastic when I was planning the lecture. And we're going to study the concepts of classical computation, which is something that I know some of you have been urging in conversations. I discovered some of you are very curious about this and want to see it. So I've decided to, take a little moment from quantum information and really dig into some of the formal definitions. It won't be very formal as usually I do, but it will be kind of formal in the sense that you're going to get a taste of what is the abstract theory of computation. Okay, not just the practical theory of computation. Some of you know how to program, and that's very different. In essence, some of the things that we consider are different from the formal theory of computation. Like experiments sometimes is different from theory. So anyway, in order to do that, to give a taste of that, I'm going to use this book, which is a reference in the course by these three guys here. Kitaev is one of the authors. Okay, and it's very nice because it starts with classical computation, and we're gonna use it. Okay, so let me share my screen as usual. There you go. So today we're gonna study the idea behind classical computation. Okay. So the first thing that we can talk about, which is the sort of elephant in the room that we always hide from this question. We never want to face it, but I thought this was a good opportunity to face it, is the question of what is information? Okay. I've recently seen an interview with Scott Aronson in which he tells a story, an anecdote about the nature of information, which goes something like this. I'm going to try to reproduce the story of Scott. I'm sorry, Scott. I hope I make justice to the story. So the story goes like this. There was some operation in the army, the US military, and they wanted to, weight. There was a project for building a war airplane, and they wanted to weight all the components of the airplane, how much it weighs, right? So you get to the wings, and then the hydraulics and all that, the internal parts of the airplane, and so on and so forth. And at some point you get to the computer, and you get to the software of the computer. How much does the software weigh? And this was back then when computers were made of these cards, perforated, cards with holes that just go down and perform the computation. We're going to see in a minute how that could work with the concept of a Turing machine. But anyway. And the general reads the report and sees that the guys who wrote it said that the software weights 0. And he said, no, this can't be something that weights 0. you know, 0 kilograms. I mean, it's impossible. So he calls up the guys and says, how much does the software weigh? Well, general, I mean, we didn't know how to answer that because, you know, it doesn't weigh anything, and it's a tricky question, what is information and so on. He says, okay, so bring me the part which is responsible for the software. And they bring the cards. And the general say, okay, let's just weight these cards and see how much they weigh. And that's the software, that's how much the software weighs. And the guys who wrote the report says, but general, you don't understand, the software is the whole. So you see, that's very, very characteristic of the elusive nature of information. Okay, so what is information anyway, right? I went to look on Wikipedia. Oh yeah, this is something about today's lecture. I'm gonna use some material, I hope this works. So Wikipedia has this very funny definition of information, which says information can be thought of as the resolution of uncertainty, which is quite nice and quite universal, you know, as a definition. Then it has this ASCII2 table here, which says Wikipedia, I think, I'm not sure. So one way of defining it, it's that which is certain, right? That's information. That is very well suited for quantum mechanics. You know, when we speak about quantum information, we say that it's encoded in qubits. Qubits have a pure state, and when they have a pure state, they have 0 entropy. And that just means that it's an eigenstate of some observable, which means that when I measure that observable, then I'm going to get the result corresponding to that eigenvalue with certainty, right? So that contains information. That's why the entropy is 0, right? Another thing that we can do is search on the dictionary. And this is the Webster dictionary I copied from an online version. And the definition of information is similar to Wikipedia's. It says knowledge obtained from investigation, study, or instruction. But it has some interesting words. Notice the word facts. And it has the word DNA and binary and computer program. The signal or character representing data. Data is also an interesting word, which also appears here. Something. Okay, it is something, right? Information, such as a message, experimental data, or picture. Okay, so this is very interesting because the definition of information on the dictionary calls for a lot of different words, okay, a lot of different things. So it seems like information has this universal character to it, right? It is not a thing because it can be all things. Can be anything. Anything can encode information, right? I mean, bits on a computer, or sketches on a notebook, or dominoes, or, you know, whatever it is, it's universal. I mean, anything really can contain information and encode information if you do it properly. Now, what is universal? I mean, I use this sometimes, and I wanted to give you some ideas, at least in this initial moment, of what do I mean by that. So examples of things which are universal, okay? So the laws of nature are universal. Okay? All things obey the laws of nature, right? Gravity is universal because all things interact gravitationally. Quantum mechanics is universal. It's a law of nature, and all the things follow these quantum mechanical rules. And information can also be encoded in all things. Anything can encode information, right? This cup of coffee, the more complicated it is, the information can be hidden from us. We can be ignorant about how it's coded, but anything serves as a way to encode information. So this is what I mean informally by universal. Okay, this is an example from this book I like. It's an interesting book by Max Tegmark. It's called Life 3.0. If you guys want to read it, I recommend. So we have a landscape here, sort of an energy landscape. And where your particle is represents information, right? Here's a bit, for example. It can be on the left or on the right. We can attribute bit 0, bit 1, okay? And you can have more complex encodings and more complex potentials. Here's another example, DNA. Okay, these four-letter alphabet are used to encode information in your DNA, which make up you, right? In Max Tegmark, he also has an interesting sentence which says, if you give enough time for hydrogen, it will turn into people. I forgot who said that, but it's an interesting sentence as well, which reflects the kind of universal nature of information. Now we can ask, what is computation? Which is the subject of today's lecture, actually. Okay, I just wanted to, give some food for thought for you guys to discuss about what the nature of information really is. Well, computation, according to Tegmark and other people as well, it's a good definition, is that it takes information and transforms it. Okay, it implements a sort of mathematical function, which can be really anything. It can be squaring a number, so you put in the number and the computer squares it, or it can be making a chess play. Okay, represent a chess position, that you have a chess position and this computes the best movement that you can make. Or it can be, you take an image and you transform it into a word. So you transform the information, okay? This is what a computer does. It's a mathematical function which takes an input and gives you an output. Okay, with possibly the answer to some problem. Of course, we give purpose and meaning to all these things. So in a sense, what we're going to do today is to try and formalize this. But this formalization is kind of, it relies on definitions, and these definitions reflect our intuitions from it, as usually. It's kind of like Newton did for force and momentum. Of course, people must have known what force and momentum are in an intuitive sense, but Newton attributed names and definitions and mathematical expressions to it. So this is sort of what Turing did for the concept of information, and for the Turing and Shannon and others, and for the concept of computation most particularly. So this is another kind of computer. It takes information from the cells and it computes things. So it takes the DNA, transcribes them into proteins, and these proteins then can exert functions. Okay, so you can see the cell as a computer. This is a good paradigm in biology, actually. Okay. So here's an example of a eukaryotic and a prokaryotic cell. It doesn't really matter. One has a nucleus and the other doesn't. DNA spread all around the prokaryotic cell. But okay, you can see them as a computer, and I'd like you to think about it that way. Okay, with all the powers of the mathematical theory of computation, right? So let's talk about algorithms. Okay. Now there's this guy, Al-Khwarizm, 825 AD, okay, and there are references that he was among the first to formalize or talk about this notion of algorithm. So what is an algorithm? Here we have to talk about algorithms, which the word originates in the name of that guy. So an algorithm is just a set of instructions that doesn't require any particular ability or intelligence to execute. Anything, any monkey, any machine, any set of gears that doesn't have any consciousness of whatever he's doing could execute those set of instructions. And it would take an input, act according to the instructions, and give you an output. This is what an algorithm is. So I think the best way to understand algorithm is through an example. Okay. So here's an example of an algorithm. My handwriting gets worse every day. So we have Euclid's algorithm. This algorithm, it outputs you the greatest common divisor, the GCD, between two numbers, A, B. Okay. Let's have a look at what the algorithm says. So you take two numbers, A, B, and you divide these two numbers A divided by B. Okay. Now you ask a question. You get the answer C. Okay. Sorry. You divide these two numbers and you take the remainder, which I'm going to call C. C is what remains of this division. Okay. So it's how many times A fits, or B fits in A, and then there's a remainder. Okay. And that's the output of this step here. Now you ask whether C is 0. Okay, it's a question. And you can have two answers. Either yes, and then the answer to your problem is B, or no. Okay. And now you make the following substitutions. You swap A to B, and you swap B to C. And you come back to this step. Now you iterate over this loop until you get C equals 0. And at this point, you output the answer equals D. So this is an algorithm. You can take two examples of numbers. For example, A equals 1365, B equals 3654. Okay, and you iterate this process here, which is what I'm showing to you here. So you divide these numbers, you get this remainder. Now you take the remainder and the smallest of the first numbers and you divide it again. You take the remainder and the smallest of the previous number and divide it again and again and again until you get remainder 0. Okay. And the last number is B, the last value B assumed, which is 21, is the highest common factor between 3654 and 1365. Okay. I took this example from also a famous book, Penrose's The Emperor's New Mind, which is something that I recommend to you. You should all read it. It's a kind of a large book, but it's classic by now. And this is one example of an algorithm. I'll leave you to it. I mean, if you haven't seen this before, just think about it. Why does it work and so on. This is an example of an algorithm, and you can see that you really need no intelligence in order to do that. Okay. Of course, you need a subroutine, which is the dividing subroutine. You need to divide. You need to know how to divide, and then you can have an algorithm for that. Okay. But let's just assume that this is a black box that you can get the answer from. You just divide two numbers. I mean, that's easy, right? Any calculator can do that. Of course, the calculator is using other algorithms, so other things similar to this one, but that execute the function of division rather than the function of the greatest common divisor. So you get a subroutine. I mean, take it for granted. And if you have this subroutine, if you have this box that does this, then you need no intelligence to execute these steps here, right? Of course, we assume that this box, which is the division subroutine, there's also another algorithm that requires no intelligence in order to do that, and so on and so forth. And that's actually, it turns out to be good, true, I mean, at least for these simple things. So there's this notion that you can come up with a machine which could execute computations. Okay, so let's try and formalize it like Turing did. Let's present the idea behind the definition of Turing for a Turing machine, which is a computer. Okay. So let's talk about the Turing machine. This is where it gets a little bit into the definitions. Okay. So here's what a Turing machine is. This is the definition. Turing machine is a collection of things. Okay. First, we're going to need a finite set which I'm going to call S. Call this the alphabet. This is the name of this set. Okay. We're going to need a blank element or character, which I'm going to denote by this symbol here. It's just a blank element. It's written nothing there. And this is part of the alphabet. There is a set A, which is part, it's contained in S in the alphabet. And we're going to call it the external alphabet. It's a subset of S. Right? We're going to need a finite set Q, which is the set of states of the Turing machine. Okay. So every element of this is a possible state the Turing machine can be in. We're also going to need an initial state, Q0, initial state. And finally, we're going to be needing a transition function. What is this? So this is represented by this delta letter. And it's a function that takes a state and a set of characters from the alphabet. And it's going to output a state, a set of characters in the alphabet, and one of three numbers, -1, 0, and +1. So there you go. That's the definition of a Turing machine. You get these 6 things, and you get yourself a Turing machine. So how does this work? Let's try to use the space here. Make a drawing. So let's look a little bit into more details. Okay, so some observations here. So the first thing is that there exists infinite Turing machines. Okay. And also you can observe that for every algorithm, there exists a Turing machine. Writing this mathematical notation just to make up some space. Right. For any given algorithm, I can come up with a Turing machine which executes it. The algorithm being encoded in all these things here, including this transition function. Okay. But what about the hardware? Okay, of the Turing machine? Let's go with step by step. So the hardware of the Turing machine, it's going to be a tape, which is a memory tape. This goes to infinity in space, or very, very, very large, okay? And there are like slots where I can write. Okay, so this is slot 0, slot 1, slot 2, la la la, slot P, okay, la la la. There is a head which I can use to manipulate the information in each slot, what is written in each slot. And there's a sort of brain, which is a sort of automaton, which is a control head, which executes the computation that the Turing machine is going to do. Okay, so this is my drawing of the Turing machine. We could have something more artistic, for example, like Penrose depicts in his book, Emperor's New Mind. So this is the Turing machine. There's an infinite chariot of tape here, which is the memory. There's a head that can alter, so it sort of can erase what's written on one slot of the tape, and it can write something else, right? And there's this black box here, which executes the function of the Turing machine, or executes the algorithm. Okay. So fair enough. Let's have a look at this. Okay, so just have a look at the definition a little bit more. Now, let's have a look at what the Turing machine does. Okay. So let's start from this delta function, transition function. So what does it do? It takes a state of the Turing machine, and it takes a letter of the alphabet, okay, which is basically a slot on the tape. Okay, and it outputs you another state, another thing written on the P slot, and the delta P, which can be either -1, 0, or 1. So what are these things telling us? So this is the current state of the Turing machine, and this is the P slot, at least what is written on it, right? Now, when the delta function, which is executed by this black box, is done, you get a new state. You write something new on the P slot, and you get -1, which means move to the left. So go to the left of the tape. 0, which means remain on the same slot of the tape. And +1, which means move to the right. Okay. So the configuration of the Turing machine starts with sigma, which is what's written on the infinite tape. It starts with a slot P, where the head is on the tape. And it starts with a state. Okay. Then we start to execute the computation. Okay. What does that mean? It means that you're going to be sent to a new tape value, sigma prime. You're going to go to P plus delta P, which is either move to the left, move to the right, or do nothing. And you're going to have a new state Q prime. Okay. Now, this is one step of the computation, one step of the algorithm. Okay. Now, if P plus delta P is smaller than 0, then you have to stop. The computer stops. It's an instruction that the Turing machine has. Okay. So you have to imagine this thing. I mean, you start with for example, with something written in the first slot and then blank spaces in all the other slots. You are at the 0th slot and you are at the state Q0, which is the initial state, and then the computation starts, blah, blah, blah. At some point you end up in a state with a tape written, a string of alphabet characters, sigma 1. You end up in slot P1 with a state Q1. La la la. And then at some point, if either of these things happen, you stop. If delta reads an undefined value, or if delta P plus P smaller than 1. Okay? So this is what the computation does. You have this mechanical device which has no clue whatever he's doing. It could be a bunch of people. It could be a DNA tape with some molecular machine acting on it. It could be bits on a computer, a bunch of transistors. They have no clue what they're doing. They're not sentient agents. They don't know. But they can execute this dull transition function here, which is you take the state, you take whatever is written on the tape element you're looking at, you output a new state, you output a new writing on the tape element you are at, and you move either to the left, to the right, or you do nothing. Okay, so you just mechanically move this tape around until delta reaches an undefined value. Okay, so you get to a point where it doesn't make any sense what the delta function is outputting, and then you stop, you just halt. Or if you start on the left of the tape, you just move around and you finally reach the other end, which means this condition delta P plus P smaller than 0. I'm sorry, I said 1 here, but I meant 0. Okay, you stop the computation. Now, what is the answer of the computation? The answer of the computation is the left part of the tape, which is contained in the reduced alphabet A, and then there's going to be some symbol, for example, the space symbol, which is not in A, And then there's going to be trash, which you don't care about. Now, this thing here, which the alphabet can be, the reduced alphabet can be, for example, just zeros and ones, is the result of your computation, which I wrote just an example there. And then there's the symbol which marks, okay, this is the end of the answer. No, you need to know that that's the end of the answer. And the rest is just trash that the machine created. Now, this trash here is very interesting. I mean, I want you to think about it from a thermodynamics point of view. You get an answer, and in order to get that answer, you need to have a lot of, you know, a bunch of trash that you don't know what to do with. It just means nothing there. It's just an output of the computation. Okay. This is a very interesting thing from the entropy point of view. So there you go. This is a Turing machine. Okay. This is what it does. Okay. Now let's comment on some things about Turing machines, some formal things. Okay. So I want to define A star as the set of all strings over A. Okay. Now, every Turing machine computes a function which I'm going to denote by phi m, which takes an element from this set A star and gives me another element in this set A star. Okay. So if I start with my Turing machine with a given input alpha, phi m evaluated on alpha is by definition the output string for input alpha. This thing here is undefined if computation, if the Turing machine never stops. Of course, no, if it never stops, then I can't define it, right? Because I don't know what it is. There's a question of what does it mean never stops, but we're in the world of mathematics here, so it's okay. We're not in the world of physics. Okay. So now I want to give you a definition with all these things in mind. Here's the definition. So a function f from the set of all strings to the set of all strings is computable if there exists a Turing machine such that phi of m is equal to f. If there is a Turing machine that executes the function f. So for any input alpha that I put on the function f, there's a Turing machine which gives me the same output that f would give, given that it was fed with that input. Okay. Now, an interesting point is that not all functions are computable. Why is that? Because consider the set of all functions f. Okay, so this is the set of all functions from A to A. So this set is uncountable. Now, the set of all Turing machines, I'm going to note this. This is the set of all Turing machines. This set is countable. Now I'm going to let the mathematically oriented of you to fill in the details of this, okay? But just it's sufficient to point out that the Turing machine is a finite thing. Okay? So it's made of a finite set of states. There's a finite alphabet. There's a finite external alphabet. And there is one number, which is 0, -1, or +1, an element of this set. Okay. And for every element of this, for every combination of these things, there is a Turing machine. And I can count them, right? I can attribute, because it is finite, I can attribute a natural number to it, which means I can count it, because the natural numbers are countable. Okay, so the argument goes along that way. Now, why is this thing here uncountable? Here's an idea of an algorithm, of a proof. Okay? So first of all, it's my idea of how to prove it. You can take an element of A star, so the set of all strings, and you can associate it to a natural number. So you can make a bijection from this to the natural numbers. It's pretty clear how to make this, right? So you just take, for example, the reduced alphabet is just 0 and 1. Okay. Now to every sequence of zeros and ones, you can associate, this is a binary number, and you can associate the natural number to it. So this is clear. Now you can use the fact that the functions from the natural numbers to the natural numbers are such that the set of all such functions is uncountable. Okay. I hope my physics notation is clear here. By this I mean the set of all functions from the natural numbers to the natural numbers. And here's a proof of that, which I found in this. I didn't know about this. It's a proof wiki. The resolution is kind of bad, but I'm going to let here the page and the name so that you copy it. You can look at the proof if you want. It's rather straightforward. So you can establish that the set of all functions from the natural numbers to the natural numbers are uncountable, and consequently, the set of functions from the set of finite strings of a reduced alphabet A to itself is also uncountable. I'm going to let you, the mathematically oriented people in the audience, to fill in the gaps. I hope some of you will be able to fill in the gaps in the lecture notes, because this would be very nice. I mean, the lecture notes that you've been producing all this time as a gift for my birthday. So anyway, this is the definition of a computable function. Okay. We can also define related notion. Okay. So here's another definition. definition of a predicate. So a predicate is just a function with a Boolean value, means either 0 or 1. 0 means false, 1 means true. So it's just a function that takes values in this discrete set of 0 and 1. So I can denote it like this. It will take a string and it will give me either true or false. Right. And now we can make another statement, definition, sorry. So P, this predicate P, is decidable if it is computable. So what does that mean? It means that I can decide whether this predicate is true or false if a Turing machine can compute it. Okay. So if P is decidable, there is a Turing machine such that P of alpha, P of a string alpha, is computable for all alpha in A star. Let me write that down. That can be. Turing machine such that P of alpha is computable for every alpha in A star. So really important to think about these definitions carefully because they are rather simple, but they're profound. Okay. So of course, in order to be decidable, P of alpha must terminate. Okay. So it has to stop at some point, right? The Turing machine that computes P of alpha has to terminate in order for P to be decidable. Okay, so you can already see that we're going towards speaking about this famous halting problem, which is Turing's version of the sort of Turing's version of Gödel's theorem. Okay. Before we close the class, I just want to give 2 more definitions about complexity. Okay. So another definition is that a Turing machine works in time t of n if it performs t of n steps for a input of size n. Okay, so this is the definition of the time of a computation. Okay, if I give an input with size n and the Turing machine performs t of n steps, that's the time that it takes for the computation to be performed. Okay, it doesn't matter physically how many seconds or milliseconds or nanoseconds or whatever time it is that it actually takes in physics, just a scale transformation. What matters is the number of steps that it has to do. There is a similar definition for space. Okay, I hope this will be clear. So the Turing machine works in a space S of n if it visits at most S of n cells for an input of size n. So this also gives you a number on how much space the Turing machine is going to use. It doesn't matter, again, how big is each slot in the tape. It doesn't matter if it's 1 centimeter or 1 millimeter or 1 hydrogen atom width across. It doesn't really matter. What all that matters is how many of these it will visit. Right? The rest is just gauge transformations, I mean scales. Okay. So now I just would like to close today's lecture with, I don't want to say that. I just want to close today's lecture with the statement, right? The main statement that we've been after, which is the Church-Turing thesis, which is not a mathematical theorem, cannot be proven. It's just a thesis, okay? You can acquire evidence to it, but you can never prove it formally. Okay. So clearly, a Turing machine executes an algorithm. Now, the Church-Turing thesis is the statement that any algorithm which is an informal notion, by the way. Okay. It's this fluxogram chart board. It's kind of informal. We know what it is, but there's no formal definition of an algorithm. The Church-Turing thesis says that any algorithm can be realized by a Turing machine. Okay. So this is what it says. Right? In a certain sense, this means that anything that you can write down an algorithm for is can be done in a Turing machine, or it means that Turing machines are as powerful as you can get. Okay? It's nothing more powerful than a Turing machine with that definition, the dual definition of that machine with the tape and the transition function. So, okay, today we've seen the definition of a Turing machine. We have spoken about the definitions of computable and decidable predicates, computable functions and decidable predicates. Informally, what the notion of an algorithm is. We discussed a little bit what information is, which is something that I hope will generate discussion among you guys. And we've seen enough to be able to state the Church-Turing thesis. Now, there's a lot to say about this. There's philosophical implications, there's practical implications for computation and things that we will ever know about, and so on and so forth. And we're going to try to explore it a little bit further down the line. Next, we're going to define what a universal Turing machine is. And we're going to talk about the halting problem and how does quantum computation sits in all this. So the ultimate goal is to go towards quantum computing, of course, which is the subject of this course. But I just wanted to give you a feeling so that you can start looking at these concepts. So just to give you an idea, okay, so a first contact with these ideas, and I hope that I have made it clear rather than confusing. So, okay guys, stay home, have fun, and that's it for today. See you all, folks.